All right, thank you for joining me. We're going to talk a little bit about sets, permutations, and combinations. What I've already got set up for us here is the set of all possible outcomes if we were to roll two dice, or if we were to roll one dice twice for each set of outcomes. And the things I want to talk about is the permutations and the combinations embedded in this set right here and how to find them. Now, one thing that we need to discuss is that when we talk about permutations, we have essentially two types. We have with replacement and without replacement. The idea of without replacement is what we're dealing when we say we're talking about putting a group of people together and we want to pick a president and a vice president on down the line. Every time we choose somebody out of the group, that person is no longer available for the next position. So if we're talking about anytime we have a scenario where the choice is being made and that choice can't be reused, that is without replacement. With replacement is other scenarios like your PIN number for your credit card or your debit card, or the permutation you use to open your phone. Even a password, for that matter, is a permutation because the order in which you use them in matters. The difference being is that with a PIN number or a password, you can reuse letters and numbers and other symbols. Ideally, you wouldn't do something like 1111 as your password because that's just silly. That's one of the, I think they did a study and they found the most commonly hacked password is 1234. I'm not sure why people would do that, but I'm sure it's simple to remember, so there's that. And if you're really not in a position where anything you have is going to be compromised, I don't guess it matters too much. But in this case, we're dealing with replacement because we roll the dice, we get a 1, we can roll the dice, we can get a 1 again. I was actually watching a science fiction show once, and they talked about this idea, and here's another scenario that kind of fits in the same idea with replacement. It is a permutation, the idea of flipping a coin 10 times and 10 times it coming up heads. And the individual is saying, well, it's the laws of physics are falling apart. That shouldn't happen. Well, the truth of it is, flipping the coin 10 times and coming up with heads 10 times is just as probable as coming up with equal number of heads and tails. That may seem a little weird, but in my finite math class, for those of you who are in there, we're going to actually look at that the next unit and see how those are actually the same event in terms of likelihood. Not necessarily the same event in terms of outcomes, but the same event in terms of likelihood. But back to the problem at hand. We have here permutations, which means the order in which we do this and matters. But we also have combinations. And this is where I'm kind of trying to distinguish between the two of them, and why when we do the formula for permutations, which is N choose R is the way we write that. There are a couple different ways you can write this. Sometimes you'll even see it written like this. And this means the permutation of N choose R, and that is N factorial over N minus R quantity factorial. And then you have combinations, which is N choose R. That should be a C, I'm sorry about that. In that case, it's N factorial over R factorial, and then the N minus R factorial, right? Now, this is with replacement, and this, of course, formula is without replacement, and that's the major difference here with these two things. If we're just doing with replacement, if you notice, you count these up, we have 6 across and 6 down. That is actually just 6 times 6, or 6 squared, which is 36 outcomes. It's a little simpler process. So this is with replacement, as opposed to this is without replacement, okay? But I'm using this as a demonstration to show what happens when we think about the combination aspects of this, which is this next piece right here, right? Why is that R factorial there? That R factorial is taking into account every pair that uses the same pieces, right? So in this instance, you have 1 and 2, 2 and 1. Those are the same piece. Those are one combination. It's two permutations, but it's one combination. Same thing with 1 and 3 and 3 and 1, 1 and 4, 4 and 1, on down the line. Anytime you see multiple occurrences of the same thing, 2 and 5, 5 and 2, those are the same combinations. So this and this are the same combination, but they are different permutations. So same combination, but different permutations. So the order in which they're being done in matters. So when you count your setup, you need to be paying attention to, is my set made up of permutations, or is my set being made up of combinations? In this case, it's being made up of permutations, and it is with replacement. So we do 6 times 6, which gives us 36, instead of this formula up here. All right? And you're like, well, can I just use the formula all the time, not have to worry about whether it's with replacement, without replacement? I don't know. Let's see. Let's see what happens. So we're going to do that. We're going to do 6 factorial, right? And we're going to do 6 factorial, then it's 6 minus, and how many we're choosing at a time here? Well, we're choosing 2, right? Okay, and when we do that, we end up with 6 factorial over 4 factorial. 6 factorial is 6 times 5 times 4 factorial. And you're like, well, how, you can just expand that? It's like, yep, you sure can, because factorial means that number times everything below it, every integer below it. And we can rewrite that as 6 times 5 times 4 times 3 times 2 times 1. Well, 4 times 3 times 2 times 1 is just 4 factorial, so we can just stop at 4 factorial. If you don't think of it that terms, you could also just expand 4 factorial out and 4 factorial on the top out and just cancel all the pieces out, because now we're left with 6 times 5, which gives us 30. They're not the same number. So you're like, so why did that happen? Well, without replacement, when we do without replacement, what we're referring to is the fact that the number of choices we have goes down. So we have 6 choices for the first one, we have 5 choices for the second one. But when we roll dice, and we roll 2 dice at the same time, or we roll 1 dice twice to get this outcome of 2 different digits here, we have the ability to reuse the same number. So here we get 6 times 5, which gives us 30 choices. Up here we have 6 times 6, which gives us 36 choices. 36 different permutations. So no, they don't give us the same outcome, because we're reducing the number of outcomes that we could get, because we're taking one out of the realm of possibilities. We've already gotten a 1, we can't get a 1 a second time. So it's going to change how this scenario looks for us quite a bit. Now, it's not a huge reduction, but it is a reduction. So if we're talking about what can we come up with, we've changed what we can come up with. And if you look at the set I've created here, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 1, 2, 3, 4, 5, 6 of them. There's 6 repetitions, 30 and 36. That's a difference of 6. So what we do is we just take out those 6 repetitions, and we have the set of all permutations without replacement. And I think that's pretty neat. So we talk about the combinations. Well, what would we get with the combinations? Well, this is interesting because we've already shown that we don't get the same thing, and the idea behind combinations is that it's a subset, all right, of permutations. So in choose R of combinations, the combinations in choose R is actually a proper subset, exclusively a proper subset of in choose R for the permutations, right? There is a lowercase r, I guess. It's a proper subset. I don't know why I put that there, I'm sorry. It's a proper subset, which means that there are elements in your permutation set that are not going to be in here. There's going to be, in this set, this permutation set, there's going to be repetition of pieces that aren't going to be here. So there's, it's going to work out a little differently for us in that instance. So when we say, well, how do we figure out the number of combinations with replacement? Well, we need to look at what are it's the same idea of, this R factorial business, right? How many times are we going to have the repetition occurring? So here's 2, 1, and 1, 2. Here's 1, 3, and 3, 1, right? We can go through and count them all. So there's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, right? And then we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. right? And I think I've failed to circle one. Oh, I circled it in the wrong spot. So when we did that, we took out all those possible repeats, right? So what's an easy way to keep track of that? Well, could we have just divided by 2 and say, well, that's just 18, right? Is that how many we end up with? So let's look at this. So we got one, and I'm just going to count the diagonal. So that shouldn't be that one. It should be this one, right? So this is diagonal of oh, that's the right one. This is the wrong one. So there's this diagonal that we're going to kind of count. So let's count the lower piece here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So that didn't work either, did it? So when we're dealing with replacement, it's actually a slightly different animal. So just dividing by 2 didn't do the trick for us. What we have to do is figure out how many of the repetitions we had, which was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 repeats. So in that instance, what we would do is 36 minus 15, which worked out to be 21 elements in that combination set. All right, so all the combinations possible is 21. All right, so that may or may not make sense. You're like, well, what's the easy way of doing that? With combinations, what we need to do is figure out some way to keep track or to count all the possibilities. In which case, we would say, well, 1, 1, 2, 2, and all those are not going to be repetitions for us. So what we'd want to do is think of all the ways that these numbers could be different. Right? We want to think of all the different ways that those numbers could be different and count all those up. And sometimes there's an easy way to do that, and sometimes there aren't. And we'll look at those processes in a different video. Thank you.